Okay. So the first step in order to draw planes is to identify the points at which the plane intercepts the x, y, and z coordinates in terms of the number of, 1 minute please. Okay, so we identify the points at which the plane intercepts the x, y, and z coordinates in terms of the number of lattice parameters. Okay, so remember that it is actually in terms of the numbers of lattice parameters, the same as we did in the direction, right? Okay, so if the plane passes through the origin, now this is different, in direction we did not do this, but in planes, if the plane passes through the origin of the coordinate system must be moved, right? And it must be moved in a way in which you end up with least number of negatives in your minor indices. Okay, how do we do that? We will cover that in the next slides. The second step is take reciprocals of these intercepts, right? Once you have identified the intercepts, then you will have to take the reciprocals. The third is clear fractions, but do not reduce to lowest integers. It's also different from the directions, right? In directions, we reduced it into two lowest integers. Here, we will keep it as it is. Okay. Am I not audible? Please raise your hands if you hear me. Okay, please remove these annotations from the screen. Okay, so, and the fourth and last step is enclose the resulting numbers in parentheses, right? For directions, it was square brackets. For planes, it should be parentheses, right? So do not make a mistake of enclosing a plane in square bracket. You will consider it as a direction. And even if your minor indices are correct, if you enclose it in square brackets and you meant planes, we will mark you 0, right? So this is very important. You have to enclose a plane in parentheses, whereas a direction should be enclosed in a square bracket. So it's absolutely necessary, right? So, okay, and the again, negative numbers should be written with a bar over the number, just like in directions. Okay, so look at this plane inside this cube, right? So if you identify, the first step is to identify the intercepts, right? So the intercepts are, if you look at this plane, so it is, intersecting this x-axis in the middle, right? So it's 1 by 2. And because we are finding it in terms of lattice parameter, so it's half of a, right? And this plane is intersecting the y-axis at 1, right? Clear? So and it is parallel to z-axis. So the coordinate points of the intercept of this plane in this unit cell are, on x-axis it is half, right? On y-axis it is 1, and because it's parallel to z-axis, so it's infinity, right? With z-axis it's infinite. Now the second step is to do what? If the plane passes through the origin, so it's not passing through the origin, right? So we do not need this at this point. The second step is to take reciprocal of these intercepts. So what we want to do is we are going to take reciprocal, right? So taking reciprocal of this will result in 2, reciprocal of 1 will result in 1, and reciprocal of infinity will result in 0, right? So these are the reciprocals of this this coordinate points. Okay, now the third step is clear fractions, but do not reduce to lowest integer. So there are no fractions, right? So it's clear. Now the last step is enclose the resulting number in parentheses. There is no negative number, so we do not need this at this point in time. So what we are going to do is we are going to write these numbers without putting comma in between and enclose it in parentheses, right? So this is your plane 2, 1, 0. Okay. So this is 210 plane. Now let's find out the Euler indices of these planes. So let's say let's find out the Euler indices of starting from A. So A is, so first of all, the first step is to identify the coordinate points at which the plane intercepts these three axes. So it is intercepting x-axis at 1, it is intercepting y-axis at 1, and it is intercepting z-axis at 1. So because the second step is to take reciprocals, so the reciprocals will result in the same thing. The third step is to clear fractions, so there are no fractions. And the fourth step is to enclose it into parentheses, right? So it is 111 plane, right? Now, if the second, let's do B, right? So B is, let's change the color, right? So B. So B, if you look at B, so B is intercepting x-axis at 1, intercepting y-axis at 2, right? 2 is actually the second, the adjacent unit cell, right? So if you draw it like this, so it's actually the adjacent unit cell, right? Clear? So this is 2. And z-axis is, you know, infinity. Why? Because it's parallel to z-axis. So what we're going to do is we're going to take this reciprocals. So reciprocal of 1 is 1. Reciprocal of 2 is 1 by 2. Right? And reciprocal of infinity is 0. Clear? So what was the third step? The third step is to clear fractions. So we are going to clear fractions. So how do you clear fractions? You multiply it with 2. Multiply all the numbers with 2. So this will result in 2. This will result in 1. And this will result in 0. Right? So in terms of Euler indices, so it's 2, 1, 0. Right? Okay. Now let's take C. So C is actually this side. So let me change the color again. So C is actually this face, right? So C, so what are the intercepts? Okay, so the intercept is because it is passing through the origin, right? So we cannot have this as our origin, because if you look at these steps, if the plane passes through the origin of the coordinate system must be moved. So the first thing we're going to do is we're going to identify our new origin. So we cannot have our origin here because the plane is passing through here, not here, not here, and not here. So what we can do is we can shift our origin from here to here, right? Clear? So now this is your X, this is your Y, and this is your Z. Clear? So C is, so what are the intercepts? The intercepts are, you know, it is intercepting it is parallel to x-axis, so this will be infinity, the first one. It is intercepting y-axis at -1, right? Because y is positive in this direction. So this is 0, this is 1, so this is -1. So this is -1. And it's also parallel to z-axis, because this is the direction, or this is the plane, and this is z-axis, so they are parallel, so it will be infinity. Second step is to take reciprocals. So this will be 0, this will be -1, and this will be 0. So the third is clear fractions, so there are no fractions, and then enclose it in parentheses and putting the minus sign as a bar over the number. So 0, 1 bar, 0, right? So this is your plane. Okay, so see, 111, 210, 0, 1 bar, 0, 111, 210, 0, 1 bar, 0. Okay, so what are we seeing here, right? So we are also here, we are talking about equivalent planes that are same. So because it's a unit cell, and the property of a unit cell is that all the unit cells should be the same, right? And all sides of it should also be the same, right? So if you take one face, right, which is actually a plane, so another face will also be similar. So this plane and this plane are equivalent because they will show you the same thing. For example, if it's a simple cube, so you will find an atom here, you will find an atom here, you will find an atom here, and you will find an atom here. So similar arrangement of atoms will be found on this plane as well. So if you look at these planes, so they are the same because it bears the same characteristics. So they are equivalent. But remember that a plane and its multiple are not equivalent. Why? Because if we take the same example, so if it's a simple cube, so you will find an atom here, find an atom here, find an atom here, and find an atom here. And the next atoms will be here, right? So now if you take this plane and take this plane, so you're looking at atoms on this plane, but there are no atoms on this plane, right? So they are different now. Clear? So a plane and its multiple are not equivalent. Why? Because the population of atoms, the arrangement of atoms on that plane, on those planes might be different, right? So they are not equivalent. Okay, so then we have another property. Let's call it property. So if you look at this, so you would find that a direction, right? HKL, I'm representing the minor indices with HKL, is perpendicular to a plane of similar minor indices, right? So it will be perpendicular to HKL, right? So HKL direction will be perpendicular to HKL plane, right? So it means that 111 direction will be perpendicular to 111 plane, right? Another example would be 100 direction will be perpendicular to 100 plane, right? And it goes for all this, right? So a similar minor indices direction will be perpendicular to a similar minor indices uh, plane, right? Okay, so what I mean is, if these are numbers are the same in both the direction and the plane, right? Like 111 is here, so 111 is here. 100 is here, so 100 is here. So they will be perpendicular to each other. You are looking at the same thing here, right? So these are the two planes. This is a plane, 111 plane. There is another 111 plane here. They are parallel to each other because they have same minor indices. And the direction, 111 direction is this one, right? Clear? So they are perpendicular. Okay, let me show it to you. Okay, please remove these annotation. Whoever drawn these annotation, please remove it, right? So, okay. Okay, so if you look at this structure, so it's a FCC crystal structure, right? Okay, so now let's draw a direction in it, right? So how do we draw this direction in this software is not part of this course. I'm just, showing you a visual of how this direction looks like, right? So let's say a new vector. So a new vector is 1, 1, and 1, right? Let's reduce this everything to 3. Okay. So you can see that, okay, so do you see this direction, right? So it's a triple one direction, right? It's a triple one direction. It's coming from this origin and it's going through this coordinate plane. Okay, let me, increase the magnitude to 6 so that you can see it through and through. Okay. So now this is the direction, right? So now let me draw a triple one plane and you would see that it will be perpendicular to this triple one direction. Okay. Okay, so what do you see, right? It's a triple one plane and it's a triple one direction. And what do you see? They are perpendicular, right? So it goes for all the same cases, right? In which you have a similar, same indices, direction and plane, you would find them perpendicular to each other. It's very important. We are going to find few problems in the problem set at the end of the chapter in which you will use this property in order to find out various characteristics, right? So how do you, where is another triple one plane parallel to this? So let's draw that too, so that you can easily visualize it, right? So one, one, and let's put it at 2. So now this is your two parallel triple one planes, right? And this is your triple one direction. Clear? Okay, it doesn't matter if it's a negative or it's a positive, right? If it's a negative, so the direction from this is positive, so this is going from here to here. If it's a negative, so it will come from here to here, right? Clear? So these are your two parallel triple one planes and a triple one direction. You can draw the same, this face will be your what? One bar, sorry, 1 0 1 bar, one plane, right? Clear? And the perpendicular direction will be what? 0 1 bar, 0 direction, right? Okay, so moving on from here, so these are the two parallel planes which I drew in that software.
Sir, can you repeat, please?
Okay. Right, these are these two parallel planes. Okay. We have
Sir,
5
can you
minutes
repeat?
remaining in this meeting. Then I will generate a new link and you will join me on that new link so that we can continue this class. Okay, so that is actually when the plane passes through the origin, you move the origin, right? We already did that, right? So this is if, there is a bar. So this is what? This is 1 1 bar, 1 1 1 1 bar plane. Why? Because we cannot have our origin here. Why? Because the plane is passing through here. So we cannot have our origin here. We have to move this origin. So where are going to be move this origin? We are going to move this origin to here. So when you move this origin to here, so now this is your z. So this is your -1. So what happens is you find x-intercept here, y-intercept here. So y is at 1, x is at 1, but z is -1. So, right? So if you look at this direction, it is moving positive in x direction, positive in y direction, but negative in z direction, right? The same goes for the plane as well, right? It is intercepting x-axis as +1, y-axis at +1, and z-axis at -1. So it is also 1, 1, 1 bar plane, right? And they are perpendicular to each other, right? You can see it from this figure. Now, as I was talking about uh, uh, equivalent planes, so all the faces are actually the same planes, right? Because you would find the same arrangement and amount of atoms on all the edges. Why? Because it's a unit cell, and the characteristic of a unit cell is that you would see it similar from all the sides, and it will be similar in all the material, right? So if you take this face, or you take this face, or you take this bottom face, or this side face, or this back face, or this front face, you would see the same thing, right? So they are all similar planes. Remember that when we talk about direction of a form, which means family of directions, family of similar directions, we enclose it in carets, right? We enclose it in carets. Like for example, if we are talking about 1, 0, 0 directions, we enclose it in carets. It means that we're talking about more than one direction. We're talking about 1, 1, 1, 0, 0 similar directions, right? But for when we write the same thing for planes, so we enclose it in braces. Clear? So now what does it mean? 100 group of planes, it's plural, right? Similar planes. So when you're talking about similar planes, so you enclose it in braces. When you're talking about similar directions, you enclose it in carets. Okay, how do you find out the distance between two parallel planes, right? So this is the relationship. The relationship is, if in general form, it is actually d HKL, because we do it for a specific plane. So HKL is equal to, these are actually the HKLs, right? Lattice parameter divided by H square plus K square plus the sum of the square of the minor indices, right? And under the root. Clear? So this is how you find out the distance between two parallel planes. We call it interplanar distance. Clear? So if you look at here, and we do it in terms of lattice, it's in terms of lattice parameter. You put it the value of the lattice parameter, and you will find out the distance between two parallel planes in terms of the units in which you have this lattice parameter, whether it's in nanometer or centimeter or meters or whatever, right? So if you look at this, so d0 to 0. So what is the distance between these two parallel planes? A divided by 0 square plus 2 square plus 2 plus 0 square under the root. So it is A by 2, and you can see it from here. This is A. This completes from here to here. It is A. So this is half of A. Okay. You can do the same for this one, right? So it will be A divided by 1 square plus 1 square plus 1 square under the root. So this will be A divided by under root 3, right? It will be